Yes. So, in today class, first of all, any doubts related to the week one, two, three? Any doubt? Yes or no?
Also,
No doubts. So, now we go to the week four. Okay, so basically, week four we start with the Boolean ex- algebra or expression. Okay, so the Boolean function or Boolean expression. Comes
Sir,
from
week 4 has been not released yet.
oh, week four not released yet.
Ah, yes, sir, week 3.
Oh, today is 18th. Okay, so it will be released on 20th. Mhm. Okay, just I will tell you about the
so we can
basic.
still do it.
Yeah.
Still cover it, right?
So Boolean function or Boolean expression. So basically, the Boolean function or Boolean expression will be defined in the two terms in a two way. One is called the mean term method. Okay, and second one is called the max term method. Okay, so first of all, we start with the mean term. The another name of the mean term method is called the SOP. The full form is sum of. Okay, like for example, we have a gate A and B. Okay, and we are using one AND gate. So the output we are getting Y. So what is the expression of Y is AB. Okay. Similarly, if we have a one more gate where we are using the NOT gate and simply this one, again I am using a AND gate and then implement these to operate a OR gate. Okay, so our first expression is what? AB. The second expression is what? B is connected with NOT gate, so we are getting a B bar. And B bar and A will be in the NAND, so it is a B bar. Finally, in the output, what we are getting the OR gate of these two outputs coming from the NAND AND gate. So AB and AB bar as an input for the NOR gate, and the output finally is what? AB plus AB bar. Okay, so this is the one term that is the product of A and B. This is the another term again product of A and B bar. Now these two product term will be combined by the sum, so it is called the sum of product. Okay, product sum of product. So basically there are the two or more than two product terms are available, and if we combine them by the summation, so it is called the sum of product. Okay, so it will be defined as a mean term as well as the sum of product term. Now the representation of mean term will be defined as a sigma with small m. Okay, sigma with small m. Now, what is the meaning of this sigma and small m? Sigma and small m is the basically summation. This is the summation, and this small will be represent the product.
Product.
Okay, which term we have to mention it here? I will explain in the later part how we represent this particular term. Now, second particularly thing with respect to the mean term is that we write a equation, write a output equation when output or basically y should be 1. Okay, only for that parts we have to represent the SOP or mean term. Clear? For an example, I have a XOR gate. This is my XOR gate. Okay, A, B, and output. For the A, B two inputs, we have four possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1. When we are getting the output 0, 1, 1, and 0. Okay, so SOP term or mean term define only for these two. Okay, SOP term and mean term define only for these two. Clear? Why only this term? Because the output is 1. The output is 1. So this is the second thing about the mean term. So first thing, mean term will be represented as a sum of product term. The representation of mean term is sigma small m. Third, it will be, we have to use only the terms where output is 0. We have to consider only those terms where the output is output is 1. Only those terms will be considered in the mean term. Okay. Now, the fourth thing about the mean term is that if any variable is represented, so it will be defined by the logic high. Logic high or 1. That is equivalent to the 1. And if any variable bar is represented, that means the output is logic low or 0. Okay. Clear? Any doubt?
Yes, sir.
Okay. Now, if we go with the again XOR gate, so basically, if you see here, we have to write the mean term only for these two parts. Why? Because the output is 1. Second thing is that if any input is 0, that will be that will be represented by the bar of that variable. Okay, or if any variable will be bar will variable with bar will be present, so we can consider that as a logic 0. So if I write a mean term, okay, so for this a is 0, so I can represent as a bar in the case of mean term, and if b is 1, I can represent as a b. Similarly, output is represented for this condition. Here a is 1, so I can represent as a, and output b will be represented as a 0, so I can represent as a b bar. Now in the form of mean term, we have to product these two. So for one term will be a bar b. Second term is product of these two. So this is the a b bar. And after this particularly product term, we have to use the summation. So a bar b plus a b bar. This is the output equation of y. or XOR gate. You already aware about this one. Okay, so for XOR gate, the Y is A bar B plus AB bar. Clear? Now, if we go with the decimal equivalent of this particularly binary number, so 0, 0 will be the 0, 0, 1 will be the 1, 1, 0, 2, and 1, 1, 3. Okay, so this Y should be also represented as sigma M, where the output will be 1 for this one and this one. So 1 comma 2. Clear? Or we can represent also Y is equal to M1 plus M2. Okay, so in any form I can represent my SOP or mean term. Now any doubt? Okay. Now for the max term. That is called the POS, product of
Sum.
sum. Okay, like we have a input A B. I am using a NOR gate. So I have a output as A plus B. Similarly, I am taking a NOT gate A, again NOR gate. So it is A plus B bar, and that will be with the AND. So our output equation is Y is A plus B, A plus B bar. Okay, A plus B and A plus B bar. Okay, so this is the one sum of A and B. This is the another sum of A and B bar and their product. So it is called the sum of product or the max term. Okay. Now if we go with the some properties of the max term, so max term should be represented in a form of pi capital M. Okay, mean term is represented in the form of sigma small m. Okay, now max term represent only when output is 0. Okay, only when output is 0. Third thing, if any variable represented in a form of A, so that means the logic low or 0. if any input variable will be defined as a bar, so that means logic high or 1. Clear? Now again we are taking the example of XOR gate. A, B and Y. 0 0 0 1 1 0 1 1 0 1 1 0. So mean term defined for these two, max term defined for these two. Okay. Now for the max term, we are taking the output as a 1. That means, output 0. So we only consider the particularly conditions where the output is 0. Now with respect to 0, if I define this variable, so here input A is 0, so I can represent as a A. B is 0, so I can represent as a B. A is 1, so I can represent as a bar. And B is 1, again I can represent as a B bar. Okay, so for this one the term is, that is the product of sum. So variable should be represented in a form of sum. The variable should be represented in a form of sum. So finally output is what? A plus B, A bar plus B bar. Okay. If you want to convert into the SOP, so what should I do? I just multiply. Okay, A bar, A B bar, A bar B, and B bar. So this is a 0, this is the 0, remaining is A bar B plus A B bar. Okay, so again a XOR gate. Clear? Now if we want to write it, so one representation is A plus B, A bar plus B bar. The second representation is pi capital M. Again, if we go with the decimal equivalent, so 0, 1, 2, 3. So where the output is 0? On this condition or in this condition? So that is 0, 3. Or capital M0 plus capital M3. So these are the three representations in a PUS form. Okay? Yeah. Now, don't be confused that SOP term is complement of POS term. These are not complement. Don't be confused that SOP term is equal to POS term, because these are not a complement. SOP term always equal to the POS term. Okay, like for example, if you see that in SOP term we are also getting the A bar B plus AB bar, and from the POS term we again represented as A bar B plus AB bar. Okay, so both term will be same, but the representation is different. How the representation is different? The sigma of M 1, 2 is equal to pi of M 0, 3. This is the only representation. Okay, so representation is complement. Representation is complement. But terms are not complement. Okay, terms are not complement. Sometimes actually the problem is that, like, given that a b bar plus a bar b. Okay, this is the SOP term is given. I have to convert into the POS form. Okay, so what should they do? They just take a complement of that one. They just take a complement of that one. Okay, so for this one particularly important theorem is defined, that is called the De Morgan's theorem. What is the meaning of De Morgan's theorem? What it says? It says that if we complement SOP term, then it will be converted into the
POS term.
POS term. Okay, and what are the outcomes of this one? Your OR gate will be converted into the AND gate. Your AND gate will be converted into the OR gate, but logic value is same. Okay, logic value is same. I just tell you this particularly thing, logic value is same. So if I am taking that a b bar plus a bar b, if I take a De Morgan's theorem, if we apply a complement of the SOP term, now it will become a POS term. So first of all, what we do when we are taking the De Morgan's theorem, we have to take step by step. Okay, so this is the one term, this is the one term. In between them, there is a OR gate. So first of all, I break these terms. So it becomes a b bar, one term, the complement of that one. This OR gate will be converted into the AND gate. And similarly, a bar, b, and bar. This one. Okay. Now, this is the one term. There are the two variables are available, a and b bar. I have to take the complement of these two. So if I complement, so this is the AND gate. Now it will be converted into the OR gate. So a bar plus b bar and bar dot a bar and bar plus bar. Okay, so it becomes a bar plus b dot a plus b bar. Okay, now you know that SOP term in the representation of XOR gate in the SOP term is what? A bar b plus ab bar. If I take a complement of that one, we are getting a POS form, that is a plus b bar, a plus b and a plus, sorry, here a plus b and a bar plus b bar. Okay, so I can say a b bar plus a bar b, that is equal to a plus b and a bar plus b bar. Now this is the POS form. Now if we go apply the De Morgan's theorem, so we apply the De Morgan's theorem of this one. This is my input, and if I apply the De Morgan's theorem, I am getting output. So that is not equal to the POS form of XOR gate. Okay. So what is the meaning of that one is that the SOP term is not equal to the POS term bar, or we can say the POS term is not equal to the SOP term and bar of this one. Okay, so I just recall that one. For a XOR gate, SOP term A B bar plus A bar B, and POS term A plus B A bar plus B bar. Whereas the complement of SOP term is what? A plus B bar and A bar plus B. So both are not equal. Okay, both are not equal. Okay, so don't be confused that SOP term XOR gate SOP representation is sigma m12, that is equal to pi m03. So here which terms are not represent here? So these are the complement. These are not a complement. These are not a complement. The representation is complement. Representation means 0 and 3 is not present here, and 1 and 2 is not present here. Okay, so we can say which are present here is not present here, and which are not present here, these are present here. So the representation is complex, basically complement, but exactly these terms are not a complement. Clear? Now we check the De Morgan's theorem's outcomes. What are the outcomes? First is the OR gate will be converted into the AND gate. So this is the OR gate. This will be converted into the AND gate. Second AND gate will be converted into the OR gate. So this is the AND gate and this one is the AND gate. It will be converted into the OR gate. Okay, but the logic value is same. What is the meaning of logic value? Here, if you see the first term, so what is the value A? A value is 1. And what is the value B? B value is 0. Because this is the SOP term. This is the SOP term, and in the case of SOP term, any variable will be represented by the 1, logic high, or any variable bar will be represented as a logic 0. Whereas in the case of second term, A will be 0 and B is equal to 1. Now if we go with the POS form, this is the POS form. Now this POS form, A bar. Okay. And now in the case of POS, any variable will be represented with the logic 0. So B will be the logic 0. And A is logic 1. Why? Because it is a A bar. For the second term, A as a logic 0 and B as a logic 1. Same, A0, B1, A1, B0, A1, B0. So that means logic value will same. Logic value is same. Only the changes is and convert into the OR and OR convert into the AND. Okay. So this is the De Morgan. Any doubt? Okay. Now I can represent this equation in a form of YAB is equal to sigma M1 and 2. Okay. So basically if we go with the input side, so this is my input side. what it shows that there are two inputs. One is the A and second is the B. Okay, but along with the input, one important information is also required, which input is the MSB and which particularly input is the LSB. Why? Because 7, like for example, we have a 6 number. If I want to convert this 6 number, so it become a 110. Now, if input sequence is A, B, C, so what is the mean term for that one? Mean term.
A.
A is 1, so that means A dot. B is 1, so B dot. C is 0, so C bar. Okay. If I change the equal sequence, B, A, C, so what is the out mean term? B as a input, A as a input, and C bar as a output. Sorry, as a input. Okay, so no changes in that one. But if I change the sequence, C, B, A, now the condition is what?
A bar,
C, B, A bar.
C, B, A bar.
A bar.
Now these two are completely different. So we can't say both are equal. So that's why when we are going to represent the variables along with the variable which is the LSB and which is the MSB, that is also important. Now this equation shows that this term will be the MSB, this term will be the LSB. If it is not given in the question that which is the MSB, which is the LSB, so always the first term will be the MSB. That means the left hand sided term will be the MSB and the right hand side term will be the LSB. So similarly, if it is A, B, C, and D, so what is the D is the LSB and A is the MSB. So don't be confused with that one, because in the gate examination, computation examination, it is never mentioned that which is the MSB, which is the LSB. Only the representation is like that one. Sigma M 0, 3, 4, 6, like for example. Okay. So it is a it is a only understandable that A is the MSB part and D is the LSB part. Now some identities we already discussed in the previous class. Identity. So some additional properties, addition properties. The properties is that if we add A plus 0, so we are getting A. No change. If we getting A plus 1, so it become always a 1. Why? Either A is 0 or A is 1. So it will be added with 1, so always we are getting a 1. Okay. Basically, this is the not a addition property, this is the OR gate property. OR gate. Okay. A plus A is always A. Okay, A plus A is the always A. And the last one, A plus A bar, that is always 1. Okay, if A is 0, so A bar is 1. And if A is 1, A bar is 0. The OR gate of A 0 1 is 1 and 1 0 is again 1. Okay, so it's always 1. Similarly, if we are going with the AND gate property, A dot 0 is always 0. A dot 1 is A. A dot A is again A. And A dot A bar is 0. Okay, so these are the OR gate and AND gate properties. So for the Boolean expressions, we discussed three important things. One is the OR gate properties, AND gate properties, and De Morgan's theorem. Now, first thing is that what is the use of all these three properties? The use of this all three properties is simplify the expression. Okay, but remember one thing: when you are going to simplify the expression, the answer never be a unique. That means different students will be getting the different answer also. Depends on the approach that you are following. On the basis of this one, the answer will be the different. So never will be the a unique solution for that. Okay. Now the thing is that why the simplification is required. Okay. For the simplification also, in the basically fifth week, we discuss one tool, that is the K-map, but we will discuss that one in the later part. But now we are going to simplify the expression. Now the thing is that why we require simplification. Why?
To increase the efficiency.
Yeah.
To increase the efficiency.
To increase the efficiency. Any other? Any other? Why we require this simplification?
Reduce the number of gates.
Reduce number of gates. Any other?
Reduction in number of gates can also result in the time reduction of time or
Yeah.
delay.
Reduce time delay. Okay. So basically, these are the reasons why we require the simplification of Boolean expression. For example, we have a B C bar plus A B C. If you are going to implement this one with the help of two input gates, so first what we do, we have to take a AB, ending of these two, AB. Now we are require the NOT gate, okay, and ending with this. Okay, A, B, C. Now the thing is that we required one more AB, add C. So here I am getting AB, here I am getting the A, B, C. This is the C bar. We are getting the A, B, C bar, and we are using a NOR gate to implement a B, C plus A, B, C bar. So how many gates we required? 1, 2, 3, 4, 5, and 6. This is the one way. Second way is that why, if AB is already implemented here, so why we require one more AB? So we eliminate this particularly AB gate and take this AB from here. Okay, because AB we are already getting here. So with the help of AB we are required. So how many gates we required? 5 gates. Okay, so we reduce one gate. Now if we simplify the Boolean expression, so from that one can I take that AB and AB will be constant from both terms? So I am taking AB as a common. Remaining is C plus C bar. Now if you use the identity, variable with variable complement, addition of these two will be the 1. So C plus C bar is 1. So the final is AB. So we required a input, we required a B input, and one AND gate. So we are getting Y. So how many gates? Only one.
Only one gate.
Okay. So if number of gate is reduced, second, with the number of gate, complexity is reduced. Third, efficiency is increased. And fourth, every particularly gate will be taking some delay. So the delay reduce. Okay, so these are the 4 reasons why we simplification is required. Okay, so let's solve some questions. Okay, so before that one, I am going to explain a 3 input XOR gate. Okay, so if I have a and B, okay, A, B, and for that one we am taking C and XOR gate Y. So we have to define the mean terms and max term. Mean term and max term. The first thing that we have to solve is mean term and max term. So the 3 inputs are available. So A, B, C. I am saying this is the Y1, and finally output is Y. So for the 3 input, how many combinations possible? Total 8 combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and last is the 1, 1, 1. Okay. Am I audible to all?
Yes, sir.
Yes, sir.
Okay. So can you tell me the output?
Yes, sir. 0, 0, 0 means Y1 will be 0.
Yeah, so basically A or B the XORing, so Y1 is 0. XORing 0.
0,
XORing 1.
1,
1,
1,
1,
1,
1, 0,
0,
and 0.
0.
Okay. Now at this particularly Y1 will be XOR with C. So 0, 0, 0, 1,
1,
1, 0,
0,
1, 0, 0, 1. Okay. So sigma m mean terms for mean terms will be defined for the output 1. So these are the 4 conditions where output is 1. Now with respect to every input, can I convert into the decimal? This is 0, 1, 2, 3, 4, 5, 6, and 7. So where the output will be 1? At 1,
1, 2,
2,
4, 7.
4, and 7. Okay. Or I can write as M1 plus M2 plus M4 plus M7. Okay, or I can write as a in term of SOP. So this one, for this one, this is the condition. So what is this term? Can you represent particularly SOP term for every input combination?
Yes.
So for the first condition, what is the SOP term?
A,
A bar, B bar, C bar.
C bar.
A0, B0, C0. So A bar, B bar, C bar. First, second,
A bar, B bar, C.
third,
A bar, B or C bar.
C bar. A bar,
B bar, A, B bar, C bar.
A, B bar, C bar.
A, B, C.
Okay. So now I can write a mean term. So that is the combination of four terms. A bar, B bar, C with the summation because it is a SOP term. A bar, B, C bar, A, B bar, C bar, and A, B, C. Okay. Similarly, if I want to write in a POS form, so this is the SOP. POS term. So these are the SOP. Now POS term. So first term POS is A plus B plus C.
Yes.
Is it clear? A plus Y plus B plus C?
Yes, sir.
Okay. The second term is
A plus B plus C bar.
A, B bar, C bar. Okay, good. So POS will be defined for the zeros. So where are the zeros? This one, this one, this one, and this one. This one, this one, this one, and this one. So POS term is what? A plus B plus C dot A plus B bar plus C bar, A bar plus B plus C bar, and A bar plus B bar plus C. Okay, and dot product between all four terms. So this is the POS form. Or I can write as a pi capital M 0, 1, 2, 3, 4 is the SOP, fifth and sixth. Or capital M0 plus capital M3 plus capital M5 plus capital M6. Okay. Yeah. Now I am taking, mm, giving you one question is that for a 3 input logic circuit, the output is logic high when A is greater than B and A is greater than B, or A is equal to B and B less than C. Okay, so find SOP and POS form.
So for SOP, I got B bar C and
So first of all, we have to draw the truth table. So
Sir,
A, B, C, 0, 0, 0.
M1 and M5.
Yeah, I will check that one. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1 1 0 and 1 1 1. Okay, so the condition is that output y is 1 when either a is greater than b or a equal to b. Okay, so this is the first condition. Okay, so a equal to b, this one, 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 and a is greater than b, this one and this one. Okay, so in these two condition, the output is 0. So first condition is fulfilled because there is a OR gate. So any of the condition will be follow. That is okay. Now the second condition is B should be less than C. So B is this one. So B equal to C, B less than C because B is 0, C is 1. So we are getting output Y1 here. Because there is a AND condition, so that means this condition follow as well as this condition. Both conditions should be strictly follow. Okay. Now if we go this one, so that condition is okay. Now the second condition is B less than C. So B and C both are equal. So 0. B is 1, B is 0, C is 1. That means B is less than C. So 1. Okay. B is 1, C is 0, greater than. B is 1, C is 1. That means equal to. That means this one is 0, this one is 0, and this one is 0. Okay. So output is 1 only for these two conditions. Okay. Now, if you are talking about the SOP term, so SOP is sigma m 1 comma 5 because it is a 0 1 2 3 4 5 6 and 7. So here the output is 1 and here the output is 1. So 1 or 5, or I can m0 plus m5. If I write equation, so y is equal to a bar because here the SOP is a0 a bar, b0 b bar, so a bar b bar and c plus m5, this one. A is 1, so a, b is 0, so b bar, and c is 1, that means c. Okay. Now POS term. All the remaining terms except these 1 and 5 all are included in the POS. So sigma pi m is 0, 1 is already included, so 2, 3, 4, 5 is included here, then 6 and 7. Okay, or I can represent as a m0 plus m2 plus m3 plus m4 plus m6 plus m7. And if you are talking about the y, so y is a plus b plus c dot, this is the first term. For the third term, a is 0, b is 1, c, sorry, dot, a plus b bar plus c bar dot, a bar plus b plus c dot, a bar plus b bar plus c dot, a bar plus b bar plus c bar. Okay. Now one more questions. A, B, and C. Okay. Find the, draw the complete truth table and find the SOP and POS term. Yes.
Yes, sir, done.
So this is the y1, y, a, b, c. For 3 inputs, we have 8 possible combination.
So we are getting it the same as the XOR gate.
So 8 inputs, yes, we check. So y1, okay. Y1 is basically 2 inputs A and B. And when y1 is 1, when both are same, because it is a XNOR gate. Okay, so for 0, 0, we are getting 1, 0, 0, we are getting 1, 0, 0, 1, sorry, 0, 0, 1, and 1. Okay, and y is what? 0, 1, 1, 0, 1, 0, 0, and 1. Okay, so if I define the SOP term, so y is sigma m 1, 2, 4, and 7, or M1 plus M2 plus M4 plus M7. Okay. Now if we already go with the this one, so again the SOP terms is 1, 2, 4, 7. So that means 2 input XOR gate and cascading of these two is equivalent to 2 input XNOR gate and cascading of these two. Okay, A, B, C, A, B, C. So A XOR B XOR C is equal to A XNOR B XNOR C. Okay, whereas A XOR B is equivalent to A XNOR B and complement of this one. Okay, so if we are taking two inputs, so both are the XOR and XNOR gate are complement. And if we are taking the three inputs, so basically XOR and XOR gate is equivalent. Okay. So either I can use a XOR gate that is equivalent to XNOR gate. Okay. So generally in the market, if you go, so 3 input XNOR gate is not available. If you go and purchase from the market, so 3 input XNOR gate is not available. Why? Because you can use 3 input XOR gate in place of 3 input XNOR gate. Clear?
Sir, one doubt over here.
Yeah.
Like the definition of the XNOR gate is yeah, actually when we have a look at the XNOR gate definition, it is defined in terms of the XOR gate. That just like we have the definition of the NAND gate in terms of the AND gate, like it is a complement of the AND gate.
Hmm.
So the XNOR gate definition also states that it's a complement of the output of the XOR gate. So, like,
This one?
if yes, sir.
Yeah.
So when we cascade it, then we'll get this particular result that we have got, that the two input XOR gate is
If we are
equivalent.
taking a two inputs for the XOR gate, so both are the complement.
Right.
Okay. But similarly, if 3 input XOR gate is available, so basically the thing is that 3 input is not possible. So what they
Right.
do, they just use this block diagram. Okay, if you are seeing the internal part of 3 input XOR gate or XNOR gate, so basically the thing is that one XOR gate of 2 input and the output of this one will be used as a third input. Okay, you are getting final output. So we can represent this one as a block diagram form, where this is block diagram of 3 input XOR gate where 3 input are given and either you output Y, A, B, C. Okay, so this output is similar to either I am using the 3 input XNOR gate, Y, A, B, C. Both are equal.
But sir, here we are assuming that okay, internally we are
Generally,
using.
the thing is that I just tell you three things initially in the starting, that we have classify our gates in three category. One is the basic gates. Okay. Second one is the universal gate. And third one is complex gate. Okay. Why we call the universal gate? Because it will be used to implement all other gates.
Right.
Okay. If we are talking about the NAND and NOR, so with the help of NAND or NOR, we can implement all gates, either AND, either OR, either NOT, either XOR, or either XNOR. Okay. Basic gates that we design with the help of transistors. Okay. And complex gate that we design with the help of basic gates. Okay.
Okay.
Now the thing is that basic gate that we design with the help of transistor, we can implement basic gates with multiple inputs. Either the two input is possible, either for if you are talking about the and or gate. Not I am talking about the not gate, but if I am talking about the and or gate, we can create a two input, we can create a three input, we can create a four input.
Yes, sir.
Okay. So I think
Yes.
you are aware with the multi-emitter configuration of transistor. Multi-emitter configuration. Okay. Normally the transistor is what? This one. This is the collector, this is the base, and this one is the emitter. This is a single emitter configuration. Similar to in this way, we can create a multi-emitter. So E1, E2, E3, E4. Okay. So I'm using the A, B, C, and D. Collector is one and gate is one. Okay. So we are creating a 4 emitter in transistor, multi emitter configuration. Okay. So we can use this as a 4 input gate. Okay.
Okay, sir.
So basic gates with the multiple input is possible. But the thing is that if we are talking about the complex gate, so basic gate along with the or NOT gate is also, because we require the A bar combination. We required a B bar combination. So that means we required a NOT gate. NOT gate, that means one input, one output. Okay, so
Right.
here is the limitation is that complex gate that will be designed with the help of basic gates is generally a two inputs.
Okay, sir.
Okay. If we are talking about the three input, so what is the meaning of that one? If A XOR B XOR C, so what is the meaning of that one? Initially, I take the A XOR B, then the output of this one will be the XORing with C.
Okay, so you
Or
cascade.
we can say B XOR C first, and the output of this one will be the XORing. Okay.
Okay, sir.
So if we are talking about the three input gate, so that doesn't mean that three input gate is basically it is a basically it will be designed, not it will be designed. It will not design. It will be only the combine of two XOR gate in a cascade form to convert into the three input gate. So for the general representation, what should I represent? I should represent this is the XOR, okay, and there are the three inputs. But if we go into the internal part of this one, what is the internal process is? Initially 2 XORing, then the output will be XOR with 3.
Yes, sir.
Okay. Similarly for the XNOR also, 2 XNOR, then that will be the XORing will start. And we can directly represent as a to representation basically. No, so we can represent a 3 input and XNOR. We can represent this one as a 3 input XOR gate. That is the only representation way. So complex gate generally with the combination of basic gates we can design the complex gate. But the problem with the complex gate is generally it is available with the two inputs. If it is available with three inputs, so what is the meaning is that first two input, okay, apply the operation of that one and use the that particularly output as the input of the second gate with another input, and finally we are getting the output.
Okay, sir.
Okay.
Okay.
Now, if we are saying here, so basically this is the a one XNOR gate. I can represent it as a XOR gate, then NOT gate, again XOR gate with the third input, and then NOT gate A, B, C. So one and one NOT gate. Two NOT gates are there. Okay, two NOT gates are available. So if we say that one we apply as a NOT gate, two NOT gates, finally we are getting a one here. Because one NOT gate will complement and second NOT gate again same. So that's why the operation of three input XOR is equal to the three input XOR. Okay, for the remember purpose only.
Okay, sir.
Clear?
Yes, sir.
Now we go to the simplification part. So we know that we are getting a sigma m 1, 2, 4, and 7. So I can represent it into the SOP form. So 1 is basically 0, 0, 1, 2 is 0, 1, 0, 4 is 1, 0, 0, and 7 is 1, 1, 1. So I can write a term for this is the A bar, B bar C plus A bar, B C bar plus A B bar C bar plus A B C. Okay. Now from the first two term, I can take as a bar as a common. So it become a B bar C plus B C bar. And from the second, these two term I am taking A as a common. So it is a B bar C bar plus B C. So it becomes a bar. Now B bar C plus B C bar is the B XOR C plus A. This is the B X nor C. Now, if you remember that in the first thing when we start, we are saying one statement is that yeah, answer never be a unique solution. Okay, so I will show you that why I say I written this term, answer never be a unique value. So this is your this step. Now the thing is that I have taken one case that A XOR B as a X. Okay, so A XOR B is what? X bar. So I can represent as a bar X plus A X bar. What is this one? A XOR X. Now what is X? B XOR C. So the answer is A XOR B XOR C. Okay, so this is the first answer. Again, go to this part and I just say that B XOR C as a X and B XOR C is what? X bar, because both are complement. So the equation should be A bar X bar plus AX. That is equation of A X nor X. Now X is what? B X nor C. That is A X nor B X nor C. Second answer. Okay. So in this way we can say that both answer on the basis of solution, how we solve, on the basis of that one it will be decided what is the correct answer. Now the thing is what? Again, I am taking first and second term and third and fourth term. Create a group of first, second, third and fourth. Now what happen if I am taking the group of first and fourth? Is it also possible? And similarly second and third. Okay. So the steps is from first and fourth I am taking C as a common. So remaining is A bar, B bar plus AB. Okay. And from these two terms I am taking C bar as a common. So it becomes A bar B plus A B bar. So that is a C A XOR B plus C bar A XOR B. Okay, so again thing is that if I am taking A XOR B as a X, so it is a C X bar plus C bar X. So it becomes A XOR B XOR C. Okay, and if I am taking the A X nor B as a X, so this representation is Cx plus C bar X bar. So that is equal to C X nor X, and that is equal to A X nor B X nor C. Okay, so the answer is same but the approach is different. So that is all up to you how you solve that one. So answer never be a unique one. So in the gate this type of question will be coming. So the thing is that you have to check which options are given. Okay, which options are given. Like for example, I am saying that sigma 1, 2, 4, 7, and the option is A XOR B XOR C. This is the one option. Second option is A X NOR B X NOR C. Third option is A XOR B X NOR C, and fourth option is A X NOR B XOR C. Okay, so you have to take both options. Okay, you have to take both options. So you have to approach all the way what is the possible solution for that. Sometimes the number solution is more than 2. Okay, sometimes the solution is more than 2. Like the question is y CBA is equal to sigma m 1, 2, 3, 6, and 7. You have to simplify and tell the minimum number of gates. Minimum number of basic gates.
Sir, two
Yeah.
inverters AND gate and 2 input NOR gate.
3 input
2 input OR.
3 input AND gate,
Yes, sir. And 2 inverter
2 inverter,
and 2 input OR gate.
2 input OR gate.
Sir, 2 input AND gate
2 input AND gate
with 1 inverter.
with 1 inverter. Okay, so let's check. So we have a 1, 2, 3, 6, and 7. Okay, so 1 is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, and 1, 1, 1. So for this one, what is the term? C bar, B bar, A. Or I can say the A, B bar, C bar. For this one, A bar,
B C bar.
C bar. For this one, A, B, C bar. For this one, A bar, B, C, and for this one, A, B, C. Okay. Now, from these two terms, I am taking BC as a common. So remaining is A plus A bar plus these two terms. I am taking B C bar as a common. A plus A bar, and this remaining term is A B bar C bar. Okay. Now A plus A bar is 1. That is BC plus BC bar plus A B bar C bar. Okay. Now from these two, I am taking B as a common. So C plus C bar plus A B bar C bar. Okay, so B plus A B bar C bar. Okay. So thing is that we required a one B bar, one C bar. Okay. Now after that we required one 3 input AND gate for A, B bar, C bar, and after that we required a OR gate for B plus A, B bar, C bar. So this answer is okay. Now the thing is that I can solve this term furthermore. How I can solve that particularly? With the use of distribution property. Okay, so we already discussed this particular distribution property in the previous class. Is that if A plus BC is given, so I can convert this A plus B multiply with A plus C. Okay, now if we want to check that the answer of this one is correct, say similar to this one, so what should I do? A multiply with A plus C plus B multiply with A plus C. Okay, multiply. So A plus AC plus AB plus BC. Okay, from all these three, I am taking A as a common. So 1 plus C plus B plus BC. So 1 plus anything is 1. So A plus BC is there. Okay, so I can write A plus BC into A plus B and A plus C form. Now, this is the A. This one I am taking as a B, and A C bar I can take as a C. Okay, A, B, and C. So I can write as a B plus B bar, A, C bar. Okay, so this is the A, B, and these two is C. So apply the distribution property. What distribution property say? A plus B. So B plus B bar. Okay, and B plus AC bar. Now B plus B bar is what? 1. So the answer is B plus AC bar. So now we required one inverter C bar. Okay, then one AND gate and one OR gate. Okay, so one inverter, one AND gate, and one OR gate. Here we can see that two inverter, one 3-input AND gate, and one OR gate. Now, can we try with the some other method also? Yes, we can try A, B bar, C bar. Answer should be different. I am not saying that you are getting the same answer. A bar, B, C bar. A, B, C bar. A bar, B, C, and A, B, C. I am using these two and these two. So first is A, B bar, C bar as it is. In the second and fourth, if I am taking the A bar, B as a common, so C bar and C. From the third and fifth, I am taking A, B as a common, so C bar plus C. So A, B bar, C bar plus A bar, B plus AB. Why? Because this is 1, this is 1. Okay. From these two, we are getting B plus B bar, A, C bar. So again, the answer is B plus AC bar. Okay, again, the answer is B plus AC bar. So the same answer. Approach is different, but the answer is same. We can try also one more method is that in place of these I am taking this one, and these two. Okay, so first and third, A C bar as a common. Remaining is B bar plus P. Second term as it is A bar B C bar. Third term I am taking as a BC as a common. So that is the A bar plus A. So it becomes A C bar plus A bar B C bar plus BC. Okay. Now I am taking a B as a common. So A C bar plus, if I am taking B as a common, so remaining is C plus C bar A bar. Apply the distributive law. AC bar plus B as a common. Now C plus C bar 1, remaining is C plus A bar. So A C bar plus BC plus A bar B. Okay, so this is also the answer. Any further simplification? Okay, so this is the answer. No further simplification is possible. So the answer is different. Okay, so you can apply any of the approach. The answer is different in every scenario. So for verification of our answer, what we do, we have to verify the options also. We have to verify the options also, that which option is possible. Okay, which option is possible. Now the thing is that when we are going to solve this type of way, the better is that we can take a options, and from option we have to calculate the SOP term or POS term. So in the next class we will discuss how we convert our Boolean expression into SOP and POS form. Okay, so we will discuss in the next class. Along with that, we will discuss the gate questions also, previous term. Now if you have any doubt, you can ask. Any doubts?
No, sir.
Okay, so we stop here.
Okay, sir.
Yes, sir.
Thank you everyone.
Thank you, sir.
I just want to take a review that are you getting
Yes, sir.
Yes, sir.
any improvement is required or any particular things I have to change for better understanding?
No, sir.
No, so that is okay. Thank
Okay,
you.
sir. Sir, can you
Thank
send
you,
me
sir.
note in GSpace?
Yeah,
Can you provide these notes in GSpace?
okay. Actually, I have saved few files, so I will share that one.
Sure, sir. Thank you,
Okay,
sir.
I am not save all the files, but I have saved some few files, so I will provide that one on the GSpace. Anything else? Okay, so thank you. We will meet on Friday.
Thank you, sir.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.